Test, 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 test. 1, 2, 3. 11 benevolent elephants. Okay, looks like things are going. Things are going well. I didn't expect Juggler to read the Saturday morning cartoon stream poll. Yes, well, you'll forgive me for checking to make sure that was working this time. So, hello everybody. This is the Saturday morning makeup stream, which unfortunately, fortunately we're finally able to do it, because this has been something we've been trying to get done for a while. I apologize for the delay, but it's sort of inevitable consequences of the universe, etc. Nobody picked robot. Oh, that's a shame. Cue robot then winning. Anyway. Anyway. I'm not sure how many people we're going to get in total. So, we'll see. But hopefully it's this is a pretty good crowd. This is a pretty good crowd. So, I have unfortunate news to share with you, Fancy Meat Computers. Due to the mysterious forces of the universe causing a synaptic miscalculation in the brain of the person who was supposed to be recording the lecture on Friday. The lecture did not actually get recorded. The person who was supposed to be recording it mistook the power is connected LED for the this camera is recording LED, and as such, it was not recorded. So it's kind of a shame, because I thought I was doing pretty good yesterday. I thought I was on fire. So this is what we're gonna do for the benefits of posterity, and for the benefits of people who were not able to attend the lecture yesterday. And I beg your forgiveness, those of you in the crowd who did attend the lecture yesterday. I'm going to quickly run through the material that was covered yesterday, not in a great deal of detail. I'm going to run through it quickly, give you the sense of it so that we can move on to the stuff we're actually supposed to be covering. It's like, I schedule this makeup stream, and then I end up having to make up two things in the same stream. It's just, ugh. Anyway, we should probably get to it. I'm ending the poll. There we go. Juggler wins! So, so on Friday, we started talking about a new, very useful algorithm, the union find algorithm. Union find is, roughly speaking, a graph algorithm that determines the connectedness of elements of a graph. So, if you imagine a scenario where you have a, I could use another run through. Yep, fair enough. So if you imagine a scenario where you have a network that's composed of nodes and edges, that's your graph theory terminology, or according to the textbook in this chapter, we call them sites and connections. So for example, if you're networking computers together, then network connections would be the connections, obviously. If it's social media, people would be the sites, and friendships would be the connections or edges. The question that you want to answer using the union find algorithm is, given a network, are two particular sites in that network connected or no? So in order to determine whether two sites are connected or not, we need to have a robust definition of connection. So when we have a series of sites that are all mutually connected by connections, we call that a connected component. You'll just hear me referring to them as components. So in this particular diagram, we have three components. 0 is a component just by itself, 1, 4, 5 is a component, and 2, 3, 6, 7 is also a component. It's a very, very important sort of fundamental. It's an important fundamental for the way these things are done, that a node by itself is its own component. Another way of thinking about this is that every node is connected to itself, right? So, so the union find, again, the union find algorithm is only interested in, well, it's interested in only these operations. So as we develop this algorithm, we're going to develop a series of increasingly efficient algorithms through a process of continuous refinement. And throughout all of this, we're only interested in being able to serve the following API. So we're going to find, as we go through this, not all of the data that we think we may need to keep is stuff that we actually need to keep, right? So our set of operations for this algorithm: connected, union, find, and count. So connected is the one that I talked about previously. Given two arbitrary sites, be silent, messaging app. Given two arbitrary sites in the network, are these sites connected by the edge of the network? Another way of construing this: are they in the same component? We also have a union operation, which is, of all of these, this is the only one that actually modifies the state of the network. How might we add connections in order to connect and merge components? We also have a find operation. Given a site, which component is it a part of? Of course, to identify which component a site is in, we need some way of identifying components. We'll get there. And count. How many components does the network contain in total? In this case, it's 3. So, I just want to have a brief word on the manner in which the diagrams are done here. So in this lecture, the visuals, at least to begin with, will center on these types of sort of rectangular networks, if that makes sense. You can see that these nodes have been roughly arranged into a grid, and that this grid, every node in this grid is connected to only one, it's only connected to adjacent nodes. But you can see a couple of components. You know, you can see there's a where's my, there we go. Boop. Like this is a component here, right? F4? 5? No, cancel. This is a component over here as well. You know, you can see that, you know, there are lots of components in this diagram. you do have to kind of squint at it though. Actually, it's kind of funny now that I'm like actually looking at this. You know that optical illusion where like white dots appear in the middle of black dots? I'm kind of getting that on this diagram. It's kind of cool. But anyway, so I just want to like put it out there that the algorithm we're talking about is more general than the structure that's implied by these diagrams, right? These nodes can be connected to as many of these other nodes in whatever fashion they want. You know, you could visualize this as occurring in three-dimensional space. You know, this is just convenient for the purposes of describing the slides. So this is like what we're going to stick to. Just keep in mind that this methodology is much more general than the diagrams would imply. So, sites and components will be identified using integer identification numbers. Connections will be identified using pairs of site IDs. So, you know, basically each one of these nodes will be labeled with a number. And, you know, to designate a connection, for example, this one between 2 and 3, we write 2, 3. Good. So let's explore this idea of connection, this connection property. So the network itself is a set of sites tupled with a connection relation. So this is your connection relation, right? It's a subset of the set of sites squared, right? Or the set of sites multiplied via Cartesian product with the set of sites. That's what that times is. It's Cartesian product. So if basically, if S and T are both members of S, and if the tuple ST is an element of the connection relation, then this is a connection which exists. It has a few properties. It's an equivalence relation, so it's reflexive, symmetric, and transitive. Reflexive just means that all sites are connected to themselves, right? So sites are connected to themselves, right? The pair SS is always in the connection relation for all sites in S. It's symmetric, so for all S and T that are elements of S, if ST is in the connection relation, then TS is also in the connection relation. Another way of saying this is that connections are bidirectional, and we also have the transitive property. So if we have, for example, a connection from 1 to 4 and a connection from 4 to 5, not only is one considered connected to 4, one is also considered connected to 5. So that's the transitive property. So here's our API for the union find class. You'll see that, you know, it's more or less as you would expect. Union does not return anything, but connects to sites P and Q, identified by integers. We initialize with the number of sites. So we have the find operation, find the component for P, are P and Q connected, and we have a count, which takes no arguments, but just gives us the number of components. So there are a couple of things that are conspicuous by their absence here. Number one, we have no way to add sites to the network after initialization. Number two, we have no way to delete connections. These are actually very important things that will simplify things. Like, this will simplify the algorithm very, very greatly. You know, after a time, you'll get used to this sort of flavor in this class. It's like, well, so you want to simplify things, eh? Well, let's start making some assumptions. So those are some of the things we are excluding so as to have an efficient algorithm. So So let's talk briefly about the union operation itself, right? Union creates a new connection between two sites if they are not already connected. So if the two sites are already connected, i.e., they already fall inside the same component, then the union operation will fail. So in this example, if we are performing union on 5,2, then we just simply create that connection. However, if we were creating union 3,7, that operation would fail. Well, it would fail because it already has a connection, right? But if we wanted to do 1,5, that would also fail because 1 is already connected to 5. You see what I'm saying? Are there any questions so far? Give me a thumbs up if there are no questions. One person says no. Well, that's good enough for the whole class then. Oh, someone does have a question. Please state your question. Okay. While I'm waiting for you guys to compose those questions, we'll just talk about how one might go about structuring that data. So, question. How are connections represented? In the slides, it uses a list. Should it not use tuples? A list of tuples. Well, that's the question that's answered by this next slide, this next couple of slides, actually, how we are actually representing connections. So, let's just continue on then, shall we? So, naive approach. Given our description so far, you may be tempted to do one of the following. This is one approach. You could store your set of site IDs in an array or a linked list, and then create a class for the connections with two fields, one for each connection point, and then make an array of references to them. That's one thing you could do. So you can kind of imagine that, right? You take all of your site IDs, put them in one array. You make an array of structs containing two things. Well, I'm using structs in this example, but like in Python, for example, you might call that a list of tuples or something like that, right? All of the connections being represented by that list of tuples, right? You could also add pointers and make it a linked list if you wanted to. Alternatively, you could make a struct for nodes and then use pointers to represent the connections. So this is like a literal interpretation of I want to directly model this graph inside of the computer system, right? Both of these approaches are terrible, at least from the perspective of the union find algorithm. They would work well if you were trying to do other things with this data. But because literally all we want to be able to do is decide connectedness, this is complete overkill. So, to come up with an efficient implementation of this, we have to have a few realizations. We have to have a few epiphanies. All right? Number one. Realization number one. These are not encrypted identification numbers. They are literally the natural numbers between 0 or 1 and the size of the network, right? Literally just the natural numbers. we can use that. Number 2, while maintaining connections numerically enables a large number of possible future operations, like, minimum spanning trees or shortest path algorithms, that sort of thing. At present, we don't need that, right? All we want to determine is connectedness. So there's no actual need to store the actual connections. And this might blow your brains apart, because it's like, well, if you don't know the actual connections, how do you know whether things are connected or not, right? Ha ha ha. You rephrase everything in terms of keeping track of components rather than connections. So, rather than associating sites with connections, let's associate our sites with components. Our data structure will then simply be a single integer array, which is much, 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 much easier and quicker and smaller, right? So in this integer array, our keys, that is to say, the number that we plug in to achieve indexing, will be the site ID. The value will be the component ID. So you can think of this array as a mapping between site IDs and component IDs. It's really important that you guys start to think about programming objects in a more mathematically rigorous, set theory type sense, right? What an array is it's a mapping from the natural numbers to some other domain, like floating point, or, booleans, or other integers, or the integers, or even other natural numbers, right? But anytime at all, you have a mapping from the natural numbers to something else, you should be immediately thinking, that's an array. Components essentially form a cycle. You'd have to tell me what you mean by cycle here. Oh, I also have another question. So can you be more specific about what you mean by the term cycle, and I'll answer this other question. Keep all sites and components, knowing that they are all connected to each other due to transitivity. So you don't have to actually keep the sites inside of the components. All you need to be able to do is, given a site, look up what component it is in, right? Which is just array lookup, which is, what's the complexity? 1, 2, 3. Everybody say it at once. Constant time, which is nice. It's nice. Constant time is the best algorithm. So, good. So, with respect to our union find class, we will have our integer array ID, which has our component IDs site indexed, and we will also have a private integer count, which keeps track of the number of components. So we won't talk about count a lot, but basically all you need to realize in order to set count up working properly is that, well, actually, let me do initialization, because it'll make more sense once I've talked about initialization. So, and this, I'm calling it right here, bing, this is the point at which we're starting new material, I'm pretty sure. Yeah, this is the point at which we're starting new material. So, the union find class we have described so far is initialized with no connections. Recall the API. So if we take a look at the API, there we go. Initialize n sites with integer names 0 to n-1, right? So basically, to set up the network, all we do is declare the array of the size for all of the components that we have, and then we put the index, we store the index at the in the value that each index looks at. Yes, so all we do is create space for the correct number of sites, n. Therefore, all connections are created by calls to the UF API post-initialization using union. Right? So the network is originally blank with respect to connections. Right? The only way to add connections is through the union operation. So we can use the properties of the union operation to make certain claims about like what the properties of the network are. So here's clarification. By cycle, I mean a set of nodes that are all connected together. Components essentially form a cycle. So that's not technically what a cycle is. Like the term cycle has actually a very specific meaning when you're talking about graph theory. I'll show you what it means very briefly. Let me just get my virtual chalkboard here. So, circles. Circles! There. So imagine this is a graph which has a bunch of nodes and no connections yet, right? So if I were to connect this graph like this, right? This graph, according to our definition of networks, is one component, right? It's a single component, obviously, because everything is continuously connected. However, according to the definitions of graph theory, it does not contain any cycles, right? In order for it to have a cycle, you would need another connection like this, right? That way you have a cycle. The definition of a cycle is basically, this isn't the exact mathematical definition, but it's like the intuitive definition. If you can start at any point in the graph and return to that point using the edges of the graph without having gone through any of those edges more than once, that's a cycle, right? So if I put one here, I can go 1, 2, 3, 4, 5, and then I'm back, 2, 3, 4. I don't know how I got to 5, right? So that's what a cycle is. So no, these are not cycles. These are connected components, right? Does that make sense? Cycle is the wrong terminology. That being said, I'm very happy that you asked that question, because it let me tell you guys what a cycle is. So, don't worry about cycles until we get to graph theory. But basically, graphs are either cyclic or acyclic, right? Trees, for example, are acyclic. Now, in this particular instance, we actually are making no claims about whether or not cycles exist in these graphs, right? So if we take a look at this example, we can probably pick out a couple of cycles very quickly. There's a cycle, there's a cycle, right? There's a cycle. Like this graph, these graphs are allowed to contain cycles, right? But a connected component is not necessarily a cycle, or does not necessarily contain cycles. Make sense? Hopefully. Good, good, good. So, all right. So, imagine the initial state of the network, right? No connections exist. What does that look like? Well, number one, all sites are connected to themselves, right? Number two, all sites are initially connected to nothing but themselves, right? The only thing they're connected to is themselves. Therefore, to initialize the ID array, all you have to do is iterate through it and initialize each element with the to the value of its index, right? Element 0 becomes 0, element 1 becomes 1, element 2 becomes 2. Another way of saying this, or another like a consequence of this, in the initial state of the network, every node in the network is its own component, and the component ID of that component is the same as the site ID. So all component IDs on initialization are the same as the site IDs. And that makes a certain degree of sense, right? Because otherwise, what are you going to do? Just pick an arbitrary number? You know? Like, in theory, you could pick arbitrary numbers for this, but, you know, even if you picked, like, random numbers to assign the component IDs, there's definitely a possibility of generating, like, the same number and starting off with a graph that's not actually disconnected initially the way that we want. And basically, the more nodes, the more sites your network contains, the more likely it is that random generation will spontaneously create a connection between two nodes, right? So, you want a bunch of unique numbers. The site IDs are already a bunch of unique numbers, so that's what we use for the initial component IDs. Does that make sense? Hopefully. So, let's talk about how our operations would be implemented. By the way, the approach to union find that we are discussing here is called quick find. It's called quick find because it makes finding quick. So let's talk about the find operation, right? Recall that find takes a site ID and returns the component ID that that site belongs to. Now that we've made our arbitrary selections about what the component IDs actually are, what is the algorithmic complexity, right? What is this? What is this operation? What do we have to do to get the component ID now that we have a site ID and we're trying to find the component ID, given that we're storing things in an array? Somebody shout it out in the chat. Big O-N. Why? It's an array, right? How long does it take to look something up in an array? There we go. Thank you. It is constant time. Yes. So when we say that quick find makes finding quick, we mean really damn quick, right? It's a constant time lookup for find, right? If we were to use a linked list, however, Abdullah would be correct. That would be a linear time algorithm, because lookup on a linked list is a big O-N algorithm. However, because we're using an array, things are much faster. Good. So, to test if two sites are connected, to test to see if they're in the same component, what do? What's the operation? And what's the complexity of that? We take their ID and see if they return the same component ID. Precisely. So connected here, right? Connected is just two calls to find plus an equality comparison. Yes. And of course, because find is constant time and equality comparison is constant time, finding out whether two elements of the network are connected is also constant time. Thank you, everybody in the chat. Exactly. Find both sites and compare their values. Precisely. Good. So you can see that quick find does find rather quick. How about union? So consider the following component mapping, right? This is a well-established graph. We've got 0, 5, 6, 1, 2, 7, and 8, 3, 4, 9 as components in this graph, right? This is what the ID array would look like. So we've got, 3 zeros, 3 ones, and 4 eights, right? Now, it's important to realize that the component IDs are arbitrary. Like, it doesn't matter whether, these were all 5s or these were all 6s. But the component ID will always be one of the numbers, one of the site IDs in the component. Because otherwise, how would it have gotten that, right? So, how... let's see. So what is the result of connected 1, 6? What would the array look like? What would it take for them to be connected? Does this suggest a procedure for connecting them? And what is the time complexity of this procedure? So how do we connect two components? So we're trying to connect. Oh, there we go. Find the values of both and see if they are different. Look for all nodes with the first value and set them to the second value. Fantastic, Brandon. Thank you. Fantastic. And I love how you remembered that we have to check to see if they're in the same component first. Absolutely. So, basically, what you do is you perform the connected operation to see if they already are in the same component. And then, if they're not, you take those two component you take the one component ID, right? You have to trace through, or you have to walk this array, looking for all instances of the first one, and then replacing it with the second one, right? So what's the complexity of that procedure? Well, to go through each one of these, like in the worst case scenario, we have to go through every single element of the array. Well, actually, in the best case scenario, we have to go through every single element of the array because, like at any point, the next number could contain another number you're looking for. So there's no, this is also the best case. Yeah, so it's big O-N. Absolutely. So, basically, we've got find is constant time, connected is constant time, union is big O-N. And yeah, so this is what this slide is doing. Simply iterate through ID, changing every occurrence of ID at P to ID at Q, or vice versa. So there is an arbitrary selection that we're making here, right? It doesn't, like, you get the same result if, in this example, you change all the zeros to ones, or if you change all the ones to zeros, right? Later on, we're going to see that that's a decision that can have algorithmic consequences. But for now, that's quick find, right? This is as good as it gets so far. So if you'd like some Java implementations of these guys, here you go. I see we're even leaving count off here. I haven't talked about count yet. So, all right. So for count then. Basically, the slides aren't talking about count at all because it's so damn simple. Although I should probably throw a slide in on it. But so if the initial state of the network is every node is disconnected, then the number of components in that network is equal to the number of nodes. Every time a connection is successfully made, the number of components in that network is reduced by exactly 1. Therefore, all you have to do in order to keep track of the number of components in the network, is all you have to do is keep track of the number of successful union operations and subtract that from the initial number of nodes. Or you could set the count equal to the initial number of nodes and subtract 1 every time union is successful, and that's count. And that also means that count is a constant time lookup. Of course, you know, if you weren't doing that, right, if you were trying to reconstruct count instead of just keeping a variable, then you would have to, you'd have to trace through the entire array, keeping track of every unique value you find, right? So that would be big O n. But fortunately, we can do it constant time by just keeping up with things as they're happening. So, for a network of n nodes, initialization is big O n. Oh, that's a mistake. That's a big mistake. Let me just fix that. Sorry, folks. That's like a... Connected is 1. There we go. Compile. Boom. There we go. So find and connected are big O1. Union is big O(n). But union is kind of an important one, right? You know, I've said before that linear time isn't necessarily terrible, right? Depends on the application. But you have to consider that, the maximum number of union operations that can occur is equal to the number of sites, right? So, to get to, a 80% connected graph, you have to perform union, 0.8 n times, right? Multiply that by the complexity of union. That means that to generate the network itself is actually big O n squared, right? Roughly speaking. So this means that for a network with m connections, the time complexity would be big O m n, which is actually, getting to be pretty bad. The quick find approach optimizes for find at the expense of union. Question. So the indexes are site IDs, and the value at the index is the component ID. Yes! Absolutely. That is, yes. 100%. Yes. So, good. So now, let's talk about quick union. Quick union optimizes for union at the expense of find. Now, you may think that this is like, maybe a dumb thing to do, because find is used in union, so wouldn't that also increase the complexity of union? Well, we'll see. It's actually quite clever. This does turn out to be better. I just want to talk very briefly, though, about the difference between lazy approach and eager approach, right? So the reason that we call this an eager approach is that when we perform union, we go in advance and set the array in order, right? With the lazy approach, we're making a very small modification to the ID array, and then we worry about making find easy. We don't worry about the find operation until we get to the find operation, basically. Is it impossible for UF to create a cyclic graph? Yes, it is impossible for UF to create a cyclic graph, despite the fact that cyclic graphs have appeared here previously. Because anytime a union operation would close a cycle, it will fail to do so because the components are already connected. So yes, it's impossible for union find to create a cyclic graph, at least if it comes to you uninitialized. And that's, what we're talking about. So yes, correct. Thank you, Andrew. Where were we? Yes. Okay. So quick union interprets ID differently, though its initialization is identical. So we're going to throw away the idea that our array points to component IDs. That's quick find, right? In quick union, each ID element is the site ID of another site in the same component. So this is kind of like turning them into pointers, except rather than being pointers proper, they simply indicate the index of another site that they're connected to, right? So, specifically, each site points to its parent node. These links form a tree structure where the root node is self-referential. So, this is how we're going to reorganize things. In our array, any node which has itself as any index which has that index as its value, that's going to be the root node of a tree, right? Then all of the rest of the sites will point to something else they're connected to, right? So if you think about the initial state of this network, every site is pointing to itself. Therefore, when you perform union, you take something's pointer and you point it to something else, but you leave the other one alone. That way it maintains its, its relationship to its parent, right? Make sense? It turns out we actually have to connect, we're only allowed to break links that are self-links here, right? So if we were to merge these two trees together, we would either have to connect 1 to 8 or 8 to 1. Make sense? So let's go through a little bit of tree nomenclature. A tree is a hierarchical data structure where each node has at most one parent and any number of children. These are not binary trees, by the way. If it were a binary tree, then each parent has at most 2 children. But since we have any number of children per parent node, this is just a general tree. A forest is a disjoint collection of trees, which is kind of a pun. And each tree has exactly one node that has no parent, which is the root node. In our case, we're kind of interpreting root nodes as being their own parent. In quick union, root nodes are distinguished by pointing to themselves as their own parent. So there you go. So that's everything. Thank you very much for your time, folks. I'll see you guys on Monday. Unless you have a quick question or something. So I've heard there are no classes next Friday, the 30th. Is this true? Yes. So if you take a look at the sessional dates, there we go. I find this is a good web page to have bookmarked at any given time. National Day for Truth and Reconciliation, no classes, Friday, September 30th. So there you go. So there you go. Is the edge directed? In this case, yes, edges are directed. At least in the sense that we will be following them back. There's kind of it's directed because you can get one, like, you can only look things up in an array one way, right? So that means that you have to go from sites to the next site index, right? So yeah, we are now working in directed edges land. For assignment 1, would the following phrase be valid for 1? Absolutely not. Parentheses must be opened before they're closed. So that's not a valid one, no. So is quick union only for trees? No. Well, see, the problem, basically the thing that quick union recognizes is that because all components, because of the way that the union operation works, all components are trees. They're all acyclic graphs. You just have to pick a root node, right? So once you pick a root node, everything can be modeled as trees, and that can improve the efficiencies of things quite a bit, as we're going to see. So the relation is not an equivalence relation in this case. The concept of being connected is still the concept of being connected has not been modified, right? It still means the same thing, to be connected. But we're not quite talking about connections. These guys are half connections in the sense previously presented. All right. Can you use java.util.linked-list to implement the stack for Q1? No, don't be lazy. Do it yourself. Don't be lazy. Do it yourself. It's not that hard. If you can't do a linked list, you don't deserve to be in second year. See you, folks.